All right, now we're going to go ahead and look at some sets theories with their names. Okay, here's the list of names. The empty set is just an empty set of brackets. Okay, there's nothing in there. Don't put a zero in there. Okay, there's another way to write it, and that's to use the, I believe that's a Swedish letter null, but we call it the null set or the empty set. Second set is natural numbers. That's pretty basic. 1, 2, 3, 4. The whole numbers is the natural numbers, 1, 2, 3, 4, but it has the number 0. How you tell the difference between the natural numbers and the whole numbers is the whole numbers starts with a whole. That's a 0. But the only difference between the whole number set and the natural numbers set is the number 0. Moving down, we have the integers. The integers are all the whole numbers plus their opposites and 0. Rational numbers have to be represented by two numbers being divided. So this nomenclature down here states that the set Q equals the set A slash B, two numbers, such that A is in the set of integers, B is also in the set of integers, and B can never equal 0 because we can't divide by 0. This little guy here is what we call the, it's like, it means is in the set of. So B is in the set of Z. How you remember rational numbers is they're all ratios, and the word ratio is embedded right in the word fraction. So all rational numbers can be expressed as fractions. Remember, like 7 can be expressed as 7 over 1, so that makes it a rational number as well. All right, let's skip down to the irrational numbers, and those are numbers that cannot be represented like a rational number. In other words, two numbers, when you divide them, will never equal an irrational number. They are non-repeating decimals with no end. They just keep going and going. Square root of 2, square root of 3, square root of 5. In fact, any square root of any non-perfect square will be an irrational number. There's a proof for that. And of course, our old friend pi and our new friend e, which we will go over later in this semester. But I strongly believe that these numbers represent something very, very important because they do not fit our number system. All right, now we're going to jump up to the real numbers. The real numbers are any number on this number line, okay, including irrationals. Let's say pi. We know pi is somewhere between 3 and 4. So that means it's in here somewhere. It's on that number line. We may not be able to pick it out exactly, but it's on there. So those are the real numbers. And here comes the grandpa of all numbers, the complex numbers, which are represented by the set A plus BI, such that A and B are both in the set of integers, and I equals the square root of negative 1. Square root of negative 1 is what we call an imaginary number. We just call it I. And all numbers known today are under the complex numbers umbrella. And there's the entire list again. Let's go ahead and see what they look like when we put them in a graph. So there's the set of natural numbers. Whole numbers contains natural numbers. Integers contains both of those. And the rationals contain all of those. Keeping on going. You got your little irrationals down here by themselves. They're lonely. They don't mind. They're irrational. They have a good time. Next one coming up is the real numbers. Right? It contains everything, including the irrationals. And the very last one is the complex numbers. Let's take the number 17. 17 can be considered a complex number because A plus BI, we could put 17 plus 0I, and that would still equal 17. So, but that's it. I hope you liked it. MGZ out.